Assalamualaikum and good afternoon. Welcome to Math series. Today we are have two talks. First one by Dr. Najmuddin. Second talk will from Dr. Alawiyah. Both of them are quite new lecturers at school here, but it's okay. They have studied left. So we will begin the first talk with Dr. Nabilah, topic of graph polynomial associated to some graphs of certain finite and abelian groups. So basically, all these are very much related to graphs and group theory. So a little bit on the background of the Nabilah. She graduated from University Science Malaysia, okay, in 2013 for her BSc, and then continued her master study at University Kebangsaan Malaysia 2015, and received her PhD recently from University Technology Malaysia under the supervision of the well-known Prof. Norhaniza, also Prof. Ahmad Irfanian from Mashhad, Iran. So I guess for more details on her biography, you can contact her personally. I would like to lay down the floor for Dr. Nabilah. Dr. Nabilah, the floor is yours, please.
Okay, thank you. Thank you, Dr. Aswad. Okay, Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon to all of you. I am Nabilah Najmuddin. I am currently a lecturer in School of Mathematical Sciences in USM. Okay, today I would like to present a part of my title, the graph polynomial, a polynomial associated to some graphs of certain finite abelian groups. The presentation will be divided into 4 sessions, which are the introduction, the preliminaries, main results, and the conclusion. Okay, as you see here, the title of my presentation is graph polynomial associated to some graphs of certain finite abelian groups. First, I would like to introduce you what is a graph. A graph, we denote by gamma. This notation equals to the V gamma and E gamma, in which this V gamma is the set of vertices and E gamma is the set of edges. If we have vertices U and V in the vertex set and E is in the edge set and E is a line connecting U and V, then we have the term adjacent, in which U is adjacent to V and E is called incident with vertices U and V. Okay, that is graph. Example of graphs. These are some common types of graphs that exist in graph theory. First is the empty graph. Here are all the empty graphs of 2, 3, 4, and 5 vertices. Empty graph means the graph contains only vertices without edges. And then we also have complete graphs. In graph theory, we have complete graphs in which each vertices are adjacent to each other. Other than those two graphs, we also have complete tripartite graph in which there are 3 partitions. Okay, and from each partition, the vertices are adjacent. But the partition here, in a partition itself, the vertices are not adjacent to each other. In group theory, there have been also many studies on graphs, but by associating them to groups. The graph is actually also contain vertices and edges, but in group theory, the graph associated to group contains vertices that represent the elements or any group of elements, maybe subgroups of the groups, and the edges are incident with the vertices based on certain properties related to the group. Among famous graphs associated to groups are the commuting graph, the non-commuting graphs that contain the elements of the group as the vertices, and we also have conjugacy class graph in which the vertices are represented by the conjugacy classes of the group. But in this presentation, I would like to highlight on the conjugate graph of the group G, in which the vertex set all the non-central elements of G where non-central meanings because a group has a center, and in order to be included into a conjugate graph, only the elements not in the center will be considered as the vertices, and the vertices will be adjacent in the conjugate graph if they satisfy this relation, or we say that A is conjugate to B. Before I proceed to some examples of conjugate graphs so you can see clearer, I would like first to highlight that there are two groups that I will consider in this presentation. They are the dihedral group of order 2n and the generalized quaternion group of order 4n. We can see that this notation is the group presentation of the dihedral group with the generators, and the relations is here. The center of D2n, denoted by Z D2n, is based on the parity of n. Whether n is odd, then the center includes only identity element, and when n is even, the center containing the identity element and also A and this element. Okay, for the generalized quaternion group denoted by Q4n, it has this group presentation and the center is this. Okay, for the conjugate graph associated to dihedral group and generalized quaternion group, you can see here. Since the vertices are the non-central elements, and for D12, n equals to 6, it is even. So there are two centers, mean from 12 elements, there are only 10 vertices, 10 elements to be considered as vertices. Okay, the vertices are adjacent when they are conjugate to each other. Similarly, for the conjugate graph of Q8, the generalized quaternion group of order 8, these are the graph. The next graph that I would like to include in this presentation is the center graph of the group G. The vertex set include all the elements of G, including the centers that we exclude just now for the conjugate graph. And two vertices A and B are adjacent if and only if AB is in the center of the group. Example of center graph associated to the first one is this center graph of dihedral group of order 10. We have all these vertices, which is actually all the elements of D10, and also the center graph of Q12 containing all the elements as the vertices. We can see here this is a complete graph of two vertices, and this is the complete bipartite graph of two partitions, K to 2. 2 here, 2 here. Okay. We have see what is graph, what are graphs associated to groups, and now we see graph polynomial. What is a graph polynomial? If we say polynomial, we know that polynomial consists of coefficients and also unknown. Okay, for a graph polynomial, the coefficients represent certain informations related to the properties of graph. Okay, in general, graph polynomial is established to examine certain aspects of combinatorial graph invariance and to characterize the structure of graphs. Graph invariance means the graph properties that are always preserved under isomorphism. Okay, in this presentation, a graph polynomial means I will include only the independence polynomial. It is a type of graph polynomial in which the information inside the polynomial related to the independent sets and independence number of a graph. Note that independent set is the set of vertices, the vertices that comes from the graph in which no two distinct vertices are adjacent. Means the vertices in an independent set will not connected to each other. Okay. The maximum number of vertices in an independent set means if we have the biggest size of independent set, then that number is called the independence number denoted by alpha gamma. To see a formal definition here, this is the formal definition. An independence polynomial is the polynomial whose coefficient is given by the number of independent sets of size k. If you see here, it is denoted by I gamma x equals to summation of ak xk, where k, this k vary from 0, the value of 0, until the independence number of gamma. Okay, here are some literature review on independence polynomial. It was the concept was first introduced by Gutman and Harari in 1983. And in 1994, Lee had introduced and defined a polynomial named independent set polynomial. However, the concept is actually the same with this concept introduced by Gutman and Harari, and hence that's I use the simpler definition of the independence polynomial. And in this paper also, Hode and Lee had determined the independence polynomial for some graph operation, meaning if we have two graphs, the operations involve like join of graph or union of graph. And then in 2000, Brown et al. Had studied on the independence polynomial of graph and found that independence polynomial of graph produce at least one negative real root. In 2014, in his master research, Perrin had studied on independence polynomials and obtained their general forms for many common types of graphs that include complete graph, wheel graph, star graph, and also cycle graph. And in 2018, Obodi et al. Also studied on the roots of independence polynomial, but they identified the class of graphs based on that non-real roots for the polynomial. Next is literature review on the graphs associated to groups. First is conjugate graph. We have Efania and Tolu in 2012 introduced the conjugate graph and discussed on the isomorphism of the conjugate graph of a finite non-abelian simple group. And then 3 years later, Efania et al. Had generalized the concept, extend the concept, and define another conjugate graph, which is called the generalized conjugate graph, and also provide some graph properties together with graph isomorphisms for the group. In 2017, these are my friends, had discussed on the conjugate graph that are associated to certain types of groups, metacyclic 3 groups, metacyclic 2 groups, and some other finite groups. And then in 2018, Muhammad Noor and Sarmin had discussed on the conjugate graph related to another type of groups, and they obtained properties, the graph invariance, such as the independence number, the clique number, and the dominating number. For center graph, in 2011, Balakrishnan had introduced the center graph, and the general forms for the center graph associated to finite non-abelian groups are presented. They obtained the general forms, and then in 2016, Karimi et al. Established a newly defined n-central graph that are related to the upper central series of a group, in which if n equals to 1, it is equal to the center graph in center graph. Some graph invariants, such as dominating, chromatic, and independence number, are also determined in this paper. And recently, the latest graph related to the center of the group is the G-central graph, where Karimi and Efania studied on its connectivity, diameter, girth, all these are the graph properties. And the G-central graph was also characterized as planar or Eulerian through specific conditions. My motivation of research comes from all this literature review, in which I saw that many graphs related to groups are studied and focus in finding graph invariants such as number of vertices, number of edges, independence number, clique number, and also there are also researchers on graphs of groups that find the topological indices and also find the energy, Laplacian energy, spectrum, and etc. There are in the graph theory itself, there are also many graph polynomials, but not yet until 2016. When I started this research, there are not yet research associating the graph polynomials to the graphs related to group. A group can have many elements, and hence the graphs associated to that group will have larger number of vertices, and this led to difficulties if we want to compute the independence polynomial or determining the number of independent sets one by one. Therefore, among the purpose of this research, I would like to simplify that process by determining the general form of the independence polynomials for the conjugate graph and the center graph associated to the dihedral group and generalized quaternion group in this presentation. Okay, here are some preliminaries that I used to obtain the main results for this research. First is theorem 2.1. We have gamma 1 and gamma 2 be two vertex disjoint graphs. Then the independence polynomial for the union of these two graphs, meaning is equal to the independence polynomial of the individual graphs. Next theorem is on the independence polynomial of a complete graph of n vertices, and the polynomial is based on these vertices. If we combine these two, then we have the independence polynomial of m complete graphs, union of m complete graphs, as this polynomial. Next is the independence polynomial of a complete of n1 plus n2 vertices, obtained as this. And if we extend the computation, you will see that the independence polynomial of a complete multi-vertex graph, a graph with more partitions, as this polynomial. Okay, to obtain the independence polynomial for the conjugate graph or the center graph in this research, I also have to determine the general form for the conjugate graph of the of both groups. First, this is the conjugate graph of D2N, obtained as the union. You see union of union of certain complete graphs, and the graphs are based on the parity of n. This is for D2N, and this is the conjugate graph for generalized quaternion group. Also, the union of certain complete graphs of certain vertices. Okay, next is theorem 2.4. This is the center graph of the dihedral group. First is when n is odd, the graph is the union between some complete graphs and complete graph. And then when n is even and n over 2 is even, then this is complete graph and also complete bipartite graph. Similarly for the last case. For the generalized quaternion group, the center graph can be obtained as this complete graphs union with certain number of complete bipartite graphs too. Okay. Now is the main results. For the main results, I used all the preliminaries that I stated just now to obtain the independence polynomial for the conjugate graph of D2N. I denote as I gamma conjugate D2N with the unknown x. Here are the polynomials. When n is odd, and the polynomial is this when n is even. From this polynomial, the degree, by definition, the degree of the polynomial, meaning the biggest number of the power of x, is the independence number. Hence, for this, we know that when n is odd, the independence number is actually n plus 1 over 2, and this one is n plus 2 over 2. How I obtain? Okay, first we already have the general form of the conjugate graph. And then we also have independence polynomial of union of graph, independence polynomial of complete graph, independence polynomial, the union of some complete graphs. By substituting the conjugate graphs, I obtain the polynomial. Next, for the case when it's even, by theorem 2.2, the conjugate graph is obtained as this union of some complete graphs. And also by using same theorem as previous case, here is the independence polynomial of the conjugate graph. For example, to see more clearer, this figure I already illustrated as figure 1. Okay, when n equals to 6, we have dihedral group of order 12, and this is the conjugate graph of D12. It has 10 vertices, meaning each vertex is belong to an independent set of size 1. So because we have 10 vertices here, we have 10 independent sets of size 1. And if we have to list one by one, there are actually 37 independent sets of size 2. Independent sets of size 2 contains vertices such as A and A4, and then A2 and A5, A2 and B. These are the independent sets of size 2. And then there are 60 independent sets of size 3, such as A with A4 with B, A with A2 and AB, something. And then 36 independent sets of size 4 include A, A2, B, AB, A, A4, A4B, A5B. And by definition, since we know the independence polynomial is the summation of AKXK, then we obtain this, we read this as 1 plus 10x plus 37x squared plus 60x cubed plus 36x, 1 plus 10 independent sets of size 1, 37 independent sets of size 2, and 60 independent sets of size 3, and 36 independent sets of size 4. Okay, on the other hand, if you use theorem 3.1 that I obtained earlier, considering the case n is even, which is n equals to 6, substituting the 6, and we obtain the polynomial. For the roots, by letting the polynomial equals to 0, the roots can directly obtain as this non-integer. Then next is on the independence polynomial for the conjugate graph of generalized quaternion group. There is only one case for all n. And then I skipped the proof because it used the same theorem and propositions as for the independence polynomial for the dihedral group. And this is for the generalized quaternion group. When n equals to 2, we have gamma conjugate Q8, which consists of 6 vertices. Hence, there are 6 independent sets of size 1, 12 independent sets of size 2. We have here A, B, A squared B, A, B, and also there are 8 independent sets of size 3. We can see A, B are independent, and then A3, A2B, A3B also independent. So by definition, we obtain this polynomial. If we use theorem 3.3, the independence polynomial of the conjugate graph of Q8 is obtained directly in a more simpler way. Then the roots of the independence polynomial also can be obtained by letting the independence polynomial equal 0, and it is just a simple calculation to obtain these two integers. For the center graph, these are the independence polynomials of the center graph of D to N. Okay, there are 3 cases. And to obtain this, when n is odd, we have the center graph of D to N as this union. There is also like argument if we use this I. Thank you, Dr. Lee. This I, because when this means like when I equals to 1, there is 1 K1. If I equals to 2, the union is of 2 K2. It is just a simple calculation. To make it more clearer, I start with 1. Okay, then by using theorem 2.1 and also the theorem on the independence polynomial of the complete bipartite graph, since this is complete bipartite, I obtain the independence polynomial of center graph of here. This is for case, and then for the second case, when n is even and n over 2 is even also, this is the center graph general form, and the independence polynomial is obtained like this. And this is the last case, okay, union. Since it is union of complete and complete bipartite, so we can use the independence polynomial of the union, independence polynomial of the complete bipartite. Okay, these are the roots obtained as non-integers. Union of the same set. Union of the same graph. Union of the same graph. Dr. Lee. First, okay. Next, these are the final theorems, last theorems. We have the independence polynomial of the center graph of Q for n, and these are the two polynomial. If we let this polynomial equals to 0, we either have 1 plus 2x equal to 0, or this equals to 0. So we have the roots as this. Okay, conclusion. This is the table of summary. Okay. In conclusion, I can see that this research actually can brought benefit to the group theory, such that the graph polynomials computed are utilized to study the properties and structures for the graphs related to groups. The graph polynomials have revealed some graph invariants, such as in this presentation, we have the independence number, the number of vertices, and also the number of independent sets of certain sizes. By establishing the general forms of the graph polynomials, it is an efficient way to discuss the characteristics for the graphs related to groups. And then by using graph polynomials, we did not need to find the algebraic properties for the group itself. We can use graph polynomials to analyze them. But I think this to really analyze, there are still more need to be done. Suggestion for future research. First, there are still many other graph polynomials in graph theory itself. And then, for instance, the matching polynomial still not being computed for the graphs related to groups, the chromatic polynomial, and the independent domination polynomial. And other than the two graphs, conjugate and center graph, there are also other types of graphs to be explored. And also, there are also other groups from group theory. I listed here some, because from the group, the algebraic properties for the group can be described as graphs, and therefore it is possible to find their graph polynomial. Some of the theorems in this presentation I have published in certain papers. Okay, you can Google my name or see my ResearchGate account. And these are my references. And for that, the end, thank you. You can reach me by the email.
Okay, thank you, Dr. Nabilah. So I guess we have a couple of questions. I'm not sure whether you have addressed Dr. Lee's questions on union of the same set, but you also have one question from Dr. Roslan. Maybe you want to answer that?
Dr. Roslan, not clear what is the main problem on graph polynomials of graphs of any types of groups. The main problems, among the problems are because we see that if the graphs, in graph theory, if we have two graphs, equal graphs, then they will have same polynomials. But if they have non-isomorphic graph usually do not have the same polynomial. We are trying to analyze more on the isomorphism of groups and how because in this research we have two groups, the dihedral and generalized quaternion. These two groups they are actually not isomorphic to each other. Somehow the graph that I chose, they are actually equal when the group order is 2 power n. Let's say group order n, the group order is 16. Then D16 and Q16 actually have equal graphs, but they are not isomorphic actually. So,
Excuse me, D16 is order is 32. D8, I think. Order, you're talking about order 16, D8.
Okay. It's the same because for my research, I denote it as D2N.
Oh,
So
okay, okay.
my presentation is D2N. And general spontaneous growth is Q4N.
Oh,
So, okay.
so N is it. I think also your when you said the your theorem is for union of disjoint sets, disjoint groups, right? Disjoint set.
Union of
Uh,
vertex disjoint graphs.
so when you talk about union of two the same groups, same sets, then they are not really disjoint sets. So then the theorem
But
is
oh, it not, you mean not necessarily disjoint? Okay.
what in response to Dr. Lee's question, lah.
Because yeah, it says that because I missed out the beginning part, so some notations I missed out. So but it
It
says
has
unit of K1. Okay, K1 you say is a graph. Graph is still a set.
Mm.
According to definitions, a graph is a set that has certain structures in it. So if unit of set, so that's why there must be something that there can be union. And then because you say you have no index, if no index on it, that's why I wonder what do you union about? So that's why I asked is whether union of the same set. If union of the same set, then it'll be only one set. Because you don't have you put the index I to n something, but you don't have but it doesn't the index doesn't play any role over there. That's why I asked is there any index there. So by say union of graph, that's why I have to go back what's the definitions of union of graph. But to me, graph is still a set. So that's why yeah. Maybe go to the because I miss out.
disjoint set.
Yeah, if disjoint set,
Disjoint actually because
if disjoint set, then unit of disjoint set is just of course lah. But of course that's why but you just put K1 over here. K1 there's only one set is there. I mean the graph, unless you see the mention of the independence of a graph, maybe I missed those definition. But the symbol means the symbol used doesn't reflect the informations you want to tell.
perhaps I will fix on the symbol.
No, that's why I see
Because
the
if
simple. I don't know.
union,
Maybe there's the way in graph theory, but I have to maybe go back to the top. There's some definition that I missed out.
union, okay, union of graph means this, like this example, we have K2, K2, union K2,
Which one is
union
K2?
K3, union K3.
Which one is
K2
K2?
is a complete graph of two vertices. This is complete graph of two vertices. Complete graph of three vertices denoted by K3.
That's what, because
Okay,
that's
if we
what, you
see,
put over there is union of K1. That's why K1 only one thing, right?
union of
Yeah.
K1 means if there are four K1 there,
Which
there
one?
will
For
be
K1.
four isolated vertices.
Maybe
Four
that's why
K1 means four
I'm not
isolated
familiar with the
vertices.
symbols for graph. But you put K1 here, you put K2, K3, K4, K5. What is K1?
K1 is an isolated vertex.
I mean,
Only
it's
one
E1.
vertex.
This E1. But you put that's why
E1,
you
yes,
put.
can be E1.
Look, that's why the symbol you have to be clear about the symbols that you want to use. Like go back, you see the symbol that make the question raised down there later. Yeah. Just scroll down. And then, no, just want to be clear on it. Though. Just yeah, because maybe there's this kind of union. The slide is not moving.
Nabilah,
Which one?
Dr. Usman
Yes.
here. E1 is empty, empty set.
Hmm?
E stand for empty graph.
Empty, huh?
So this one E2 is empty graph with two vertices.
Two vertices.
Two vertices.
Two
E3 is empty
vertices.
graph with
E3
three
is empty
vertices.
graph
Okay.
with three vertices.
K2 is there's a definition is fine. That this is but what I want to ask is just now is talk about the union of the K1. From I equal to 1 until n minus 2 over 2 or what. So that's why I want just to understand what you're trying to union over there. And the definitions of independence, maybe I've missed it. What do you mean by the two graphs are independent?
Not two graphs independence. The vertex are independent. Like this vertex A independent with B.
Sorry, which okay, this figure one is a one graph, right? So got
Okay.
A5
Okay.
is another vertex.
A5 is another vertex. Yeah.
Y equal A5, but doesn't matter lah. So yeah, there are one, two, three, four.
Why I call this? Because this is from group theory. This is element of group D12. The hydrogen
Yeah,
group of order
okay.
12.
So there are 10 vertices there. Okay. Then of course the relations of this one come from the relations in group theory, because this is dihedral group, you say. Okay, what's the relation here? I don't know, conjugate.
Conjugate this.
A conjugate with A5, because I forgot my group theory already. Okay. So the conjugacy of this thing. Okay, and then so now that's why later go to the union. I just want to understand what
The union means
the symbol that you use just later. That's I raised the question just now. Go down, I think. Go down in one of your theorem. Not the theorem. Here. Not this one. Here. In theorem 2, 2.2. You see, that's why you union I equal to 1 of K2. You know, you also have K1. So that's why, what is the thing that you try to union here?
The union of K2. They are actually, in this graph, there are n minus 1 over 2 complete graphs of order 2. There are n minus 1 over 2 K2, the union. There are...
Maybe that's why this is the way that you have to explain what it means. Yeah, that's why you just put K2. Then you have to, there should be a way to. So you meaning, I think you try to say that in K2 there are n minus 1 over 2 different combinations, or different what of K2?
Different.
Yeah.
No, not different. Means if we have n, this is n odd, n equals to 5. So we will have 5 minus, so we will have 2 K2 union with 1 K5.
So what is those 2 K2?
Those two.
Yeah, when n equal to 5, you say there are 2 union of 2 K2.
The 2 K2 is the graph K2, but the vertex labeled based on the elements in D10, the hydrogen group of order 10.
I think you better you list out the example there only you can see. Otherwise, you put like this, they can raise it, because I don't know where this is your symbols or what. Like just now you say, give a concrete example when n equal to 5. So what are those 2 K2 that you try to talking about, and how they union with the K5, and how you come up with the I of the gamma. And then how do you get all these things? So you over here n equal to 6. So what are those? So 6 is even. Then what is that? Sorry, go back to the formula. The previous formula. Yeah. Go back to the previous formula. You take n equal to 6, right?
Yes. N equals to 6.
Yeah, what's the formula?
We have union of 2
so
K2.
6 minus 2, 3. So 3 of K2. What are those 3 K2?
3 K2, 2. 2 K2.
It says 6 minus 2 divided by 2, the 3 of them. Union of 3 K2. I don't know what. That's why what this
union of 3. There are union of 2 K2 with 2 K3. Yeah.
2 K2 and 2 K2. Yeah. So what are those 2 K3?
What are those?
Yeah. What are those 2 K2 you're trying to talk about? Yeah.
Dr. Lee, Nabilah. Okay, the definition of, we know that the definition of the union of two graphs, let's say we have like two graphs, let's say G1 and G2. So it is a graph where we union their vertex set and their edge set. So it means that the graph that we obtain depends on how the vertex set and the edge set looks like. So if we have like the vertex set of the two graph are totally disjoint, then we will get the union of the graph of G1 and G2. We will get like two, if the vertex set are totally disjoint, then the graph that we obtain is like we call disconnected graph, means that we will have two pieces, like two set of vertices, because the vertex set are disjoint. But if some of the vertices are the same, means that we label some of the vertices from G1 and G2, we have some, like if we have A in G1 and then we have also A in G2, then what we will get is like one piece of, our graph that we get is a connected graph, just one component only. If the vertex is disjoint, then we will have like two component. Right. That is how we define the union of two graph thing.
Okay, good. Yeah, that's why you do give example, then you have to go back to the formula. How is it? You give a concrete example to show it how those things work. Okay.
I think I missed out the general form here to compare to the graph. Yes.
It has to. That's the reason I asked, because when not clear where to use the example to illustrate it, and all this, I feel is important so that, because you give very short, that's why it's the time to illustrate everything, so, easier to follow. Okay. Yeah. Okay. Thank you.
For the question by Dr. Roslan, difference between graph polynomial problems with polynomial of graph of group. Not so much difference, because we pretty much the same, but it's just that because the graph associated to groups represent the algebraic properties of group, so we are looking forward to actually try to make more analysis on the group properties by using graphs and the graph polynomials.
So any further questions from the audience? Maybe if you don't want to put in a chat box, maybe you can unmute yourself.
Dr. Nabilah. Just one question. Go back to your slide before this. The theorem on the conjugate graph. Okay, this one. Theorem 2.2. So this one you obtain the result on the conjugate graph in terms of K2 and Kn. So the union K2 with Kn. So this is actually disconnected graph, right? Right.
Disconnected.
Right. So is there we always obtain the conjugate graph in terms of disconnected graph? What happen if you consider other graph of this one, conjugate graph of D2N, the hybrid graph, the hybrid group?
Do you mean conjugate graph only or other type of graphs? For other types of graphs, it does not necessarily.
Other type of graph.
No, it can be. There are kinds of obtaining star graph, but still they are still trying to generalize, and among the component in their graphs are the star graph.
Any specific reason why we obtain the disconnected
No. For now, no explanation yet.
Yeah, maybe once you obtain the graph structure, right? Graph structure for conjugate graph of D2N. Then you see that the structure is disjoint or disconnected. Then the graph looks like the combination of K2 and Kn, and disconnected or disjoint as well, right? Then you form, right? You express the graph in terms of K2 and Kn, right? or the reason why you obtain disconnected graph here? Is that the reason?
No, we did not determine the disconnectivity, but when we list the elements of the group, and then we make them as vertices, and then when we put the relations such as two vertices are adjacent when they are conjugate, then the graph forms this graph. So we are still, this is still work in progress.
Ongoing, yeah?
To explain why, why it becomes like this and like that for now,
So need to be explored more,
Yes, betul.
Assalamualaikum. Azhana here. Maybe I can answer a bit on Dr. Roslan's question. Conjugation is already a partition. Kalau in group, you partition the elements to classes, kan? So that's why you obtain a disjoint graph for your conjugate graph of the group. I think all disjoint, right, Nabilah?
Yes.
Yeah, because conjugation, you already partition the elements to classes. So you obtain this disjoint graph lah, because from the group itself.
Dr. Azhana, if not disjoint, cannot. Dr. Azhana.
Kalau
It can
conjugate,
be.
kalau it's in conjugate class, you already you already partition the elements. So no joint elements.
If Dr. Roslan is looking for disconnected graph, I obtain the non-commuting graph of dihedral group. They are connected graph, but in the form of complete multipetite graph for non-commuting graph.
So what is the applications of these studies? Why you look at the conjugate graph of it, then from there what information you want to get about the group?
I actually was trying to compare the graph of the three groups, and then to see if graph polynomials can explain something, like just to explore more on the properties in graph theory, the topics in graph theory, because since in graph theory, when a graph is formed, among the topics studied are the graph invariance. Some of my friends did on topological indices on the graphs, and I did the graph polynomials to see the relations. Maybe I hope that one between the relation between the three groups, but by using the graph polynomials. Or maybe if I can define a new graph polynomial that can explain on the properties of the groups, I will.
For example, what people have done before, you see, of course, in group theory, the relations of the group, I think I don't know, only under the isomorphism or whatever, they only, you talk about the relations in group theory using isomorphism. So then this polynomial, so I don't know, I just asked because, of course, I know, group and graph theory, they are the roles between each two of them. So I just want to, understand what actually they want to see. Because if things can be studied in already using group, then what's the thing that you want to use in a graph? Of course, there I see in general there's something called the topics of geometric group theory that's using the graph of groups. Okay, so there are something else they try to. Of course, I see they use a lot of fundamental groups. There are more things to. By just that's why, just curious by just researching this. But just now, Nabilah also say, yeah, the coefficients of the polynomials represent what do you say? I forgot already.
Number of certain information of the graph, like maybe number of independent sets, number of cliques, depending on the type of graph polynomial.
Yeah, but you see, but it comes from the group. That's why how is it related? You know, the clique of it is under graph theory, and yeah, there have to be clear lah. All these relations, what is the purpose of this? To me lah, you know, so that then you should understand what you are trying to check about. You know, just some suggestion I see. Because if you keep on looking at different types of groups, you have to see, you know, what is the things. Like for example, the conjugate graph says the number. So how does it connect with the group? Because you're doing on the Q4, for example, I just look at theorem 2.3. So from this, okay, for the result, so what can you connect? Is this something the same that, you can get the same information by using group? Now also you can get the same information when you use the point of view of graph theory or what? I don't know. I really say conjugate graph.
No.
Never mind. Thank you.
But what you say is true. I also think about that.
Roslan might want to say something. Just now.
Dr. Nabilah, actually at the end, you want to go for more, right? More information on graph or a group or both of them?
I think both.
The properties of information on graph or a group, or relation between graph and group.
Relation.
See, okay. Is there any good research done so far on the related to your research in this related to this research?
Any what?
Any good papers or good research? Maybe somebody from Iran, for example, doing this.
Oh no, not sure. Not
sure.
Tak sure. Tapi macam tak ada, belum je.
Still new lah. Got some papers, some related papers, right?
Related papers, but from graph theory papers. Banyak graph theory papers.
So group theory tak banyak, not much.
Group. Tapi is on the graphs of groups only.
Okay. So consider new lah.
So, any further questions or comments? Okay, so we're already at 3:25, and it's such a fruitful discussion, and I hope that discussion will bring a lot of new ideas, new concepts, and maybe Dr. Nabilah can refer to Dr. Lee, Zahna, and Prof. Roslan to further extend this, what I, on my point of view, can be considered to be a novel area of research lah. Since you said that there's not much good paper yet out there, so maybe it's time for you to shine. So I guess that's the end for the first part of this evening talk, and maybe we can take a short toilet break for 5 minutes before we proceed with presentation from Dr. Alawiyah. So thank you, Dr. Nabilah, and we'll see you in 5 minutes.
Okay, thank you, Dr. Aswad.